So when we start with the governors, generally what is a governor? Governor is a feedback device, right? The governor is a generally feedback device. So generally there will be, when there is a variation in load, then that variation in load will be sensed by the governor, and governor sends the signal to the feedback device, throttle valve. So that throttle valve will increase the fuel supply, decrease the fuel supply depending upon the variations of the load. Generally when we show the two graphs, first one will be the graph between the efficiency and the speed. If the speed is increasing, then the efficiency will increase, but at one optimum the efficiency will maximum and the efficiency will decrease gradually. And when you see about the load, if you talk about the efficiency of the governor, so there will be omega optimum. The loading is increasing, so for one load there will be one omega optimum. Okay, so so generally what happens, as a load is going to increase, then the mean velocity, mean speed is going to decrease. All right, so if the speed is going to decrease, then the fuel supply, if the speed is going to decrease, then what the governor will do, governor will sense the speed reduction in speed, and it sends the feedback to the throttle device, and throttle device will increase the fuel supply, and the omega optimum will be achieved. Suppose if the load is decreasing, then omega speed will increase, so that speed is sensed by the governor, and governor sends the signal to the throttle device, and the fuel supply is controlled in that way. Okay, so generally when we look at the diagram, when we look at the figure, let A be the fluctuation of energy of the governor A. So when as we see as we compare the governor A and B, there will be there is less fluctuations in governor A when compared to the governor B. All right, so governor A permits so there will be fluctuations, right? So why there is a fluctuations, why can't the fluctuations can be zero? So generally when we look at in the practical manner, then the governor is a feedback device, right? So it must sense the reduction in speed. While sensing the reduction in speed, and while sending the message to the throttle device, so it takes some time. Okay, if we assume the time is negligible, then the throttle valve has to supply the fuel, okay, to meet the demand of the load. So while supplying the fuel, it will take some time, right? So that's why there will be fluctuation. The governor which has less fluctuation is known as the efficient governor. Okay, so the governor so what happens during the fluctuations? The vibrations will increase. Vibration in the sense oscillations will increase. So generally when the oscillations are going to increase, those are dynamic loads, right? So governor is subjected to the dynamic load. Strength of the governor is going to decrease. So that's how the strength of the governor is going to decrease. So we need to minimize the fluctuation. We can minimize the fluctuations, but we can't make the fluctuations to zero. All right, so this is about the use of the governor and concept of the governor. Okay, so generally what is the difference between the flywheel and the governor? Flywheel acts as a reservoir. Okay, when there is a generally when we see the strokes, 4 types of strokes: suction, compression, power, and exhaust stroke. Suction requires some amount of energy, and compression requires some amount of energy, that is power consuming strokes. The power stroke is a power producing strokes. Okay, so generally in the power production stroke is only one stroke. So that's why what we need to do, we need to utilize the power of the stroke with the help of there will be a rotational kinetic energy, there will be excess energy. That rotational kinetic energy we are using in the terms of flywheels. Okay, we are choosing one disc or wheel type flywheel. Okay, depending upon the moment of inertia. If the moment of inertia is greater, then the fluctuation of speed will be less. Okay, so higher moment of inertia flywheel we are choosing disc flywheel. So that flywheel will supply the energy in all the required cycle. It will take the excess energy, and supply the energy when there is a deficient of energy, right? Flywheel acts as a reservoir of energy, whereas governor is just a feedback device. Okay, there is no control over the fuel supply when we talk about the flywheel, but governor controls the fuel supply by sending the signal to the throttling valve. Okay, so also a flywheel is continuous working device, right? It must supply the fuel in the it must supply the energy in all the cycles. So governor is an intermittent device. Okay, it is only when the required load is increasing or decreasing, then the governor's work will come into picture. Okay, that is the thing. Next thing, it is intracycle fluctuation like flywheel. When the power stroke is going on, flywheel can store the energy when we start the flywheel, okay, and other cycles it can supplies the energy. But when it comes to governor, in the power stroke, the fuel supply can't be increased, and in extra stroke, fuel supply uh, can't be increased, but only in suction stroke the the fuel supply can be increased, okay, fuel supply can be increased. Therefore it must wait when the suction comes. It is going on the power stroke, the load is increasing, in the sense it will not supply the fuel at that power stroke, right? It must wait till suction stroke comes. When suction stroke comes, then it supplies the fuel, more fuel, okay. That's how these things are going on within a less fraction of seconds. It must wait to the next cycle, in the sense we are not waiting for 5 hours 6 hours, okay. It is within fraction of seconds it is happening, okay. So inter cycle fluctuation we can call it as, okay, between two consecutive cycles it is working. All right. So and the thing is that a flywheel does not depend upon the type of stroke, right? Also flywheel no control over the speed. Flywheel does not control the speed, but governor will control the speed. Governor will control the speed. Governor will control the fuel supply, okay. Flywheel will not do these things, okay. Generally when we look at turbines and all, then flywheel may be required, may not be required, okay, depending upon our requirement. But the governor is necessary for each and every device, so okay, each and every prime mover. Turbine is also prime mover, so governor is required for each and every prime mover, because there is a fluctuation of load, right? Prime mover will raise the load, okay. There will be certain turning moment, torque which is need to be overcome, okay. So there will be fluctuation of load. If once there is fluctuation, there will be fluctuation of speed. To maintain the speed constant, then we must use the governor. So when we see, when we look at the first governor, that is watt governor, okay, and then there will be certain arrangement of this governor, okay. So as we can see in the figure, there is a sleeve, there is an engine shaft, there is a spindle, okay. To the spindle there will be balls are attached of certain mass, and there will be certain mechanism which is there in this watt governor, okay. So generally engine shaft rotates with omega, then spindle will also rotate with omega, because velocity ratio is 1, okay. So as the governor valves will rotate, then there will be centrifugal force will be comes into picture, okay. Due to the centrifugal force, the radius between the two valves is going to increase. So this motion is transferred to the sleeve, okay. As the speed is increasing, then the MR, that centrifugal force will increase. Due to the centrifugal force, the balls move outwards, okay. The radius will increase. So that's how the sleeve is going upside. When the sleeve goes upside, then there is a mechanism, that motion is transferred to the bell crank lever to the throttle valve, and the throttle valve will close, okay. Then the fuel supply will decrease. Once the load is going to increase, then the omega is going to decrease. Once the omega decreases, the centrifugal force decreases. Due to the decrease of the centrifugal force, the radius of the ball decreases. Once the radius of the balls decreases, then the sleeve will move downwards. When the sleeve move downwards, the throttle valve will open and the fuel supply is supplied, okay. This is how the governor is going to work. So generally when we look the analysis of the governor, okay. So let's first of all discuss about the governor types, okay. But what governor types? Let's introduce one thing, okay, that is the height of the governor. Height of the governor is the distance between the midpoint of the distance between the point of the mass where two masses are intersecting, and the topmost point. That is, when the top links, when the top links are intersecting, there the distance between the point where upper arms are intersecting by 1 are extended, okay. That is the height of the governor. Suppose open arm type governor have you seen? So there will be when you extend the links, then at one point they will intersect with each other. From that point to at the middle of the point, that is the height of the governor. In the cross arm type also, when the arms are intersecting, there we can say that at that point, from distance between the point and center of that governor is known as the height of the governor, okay. Generally when we are analyzing the governor, sir, omega will be directly proportional to 1 by under root of h, all right. From the analysis, generally what we are doing, there will be eye centers, right. eye center at A and eye center at B. We are not naming the eye centers. We are not naming the links. Therefore, we can't name the eye centers. But eye centers will present at these two positions. Okay. So generally, when we according to analytic theorem of three circles, okay, the three eye centers will be in line, right? So one eye center will be at some fixed distance from these two eye centers. Okay. So intersection of these eye centers can be given by that eye center can be given by I. So now the eye center is nothing but at that point the velocity will be 0. All right, and also the moment about that point will be equal to 0. Summation of the moment at that point we can take it as 0. Okay, when the body is in equilibrium we can take at hinge point or at any point. When the body is in equilibrium, when the body is moving, it is not in equilibrium, we can't say that at one point the moment summation of moments are not 0, because there will be resultant force due to which the body will not be in equilibrium. There will be some unbalanced force, right? So therefore moment equilibrium method can be applied only for the body in equilibrium. So that's why we are not applying for B and A, right? So we can apply when the body is in equilibrium, right? So I is a point where the moment summation of moments will be 0, and in what governor we are considering sleeve as massless. Therefore there is no eccentricity first of all, and there is no mass of the sleeve is considered. The mass of the sleeve is considered, then that can be taken as mg by 2. Okay, from one side. Okay, so while solving this geometry, where theta is the angle made between the mass mg and that eye center, hypothesis of the eye center. So the one relation will come that omega is directly proportional 1 over the root half. If we draw the graph, we can see that once the that thing, what we call once the wait, that will be disturbance. Okay, once the what I was saying. Okay, so when the omega of the governor is increasing, then the distance between the height of the governor is also increased. Okay, at one omega, the distance between the sleeve is the distance covered by the sleeve is very less. So therefore we can't be able to control the fuel supply. All right, fuel supply. Therefore we can say that at one speed it is valid up to only one speed, that is 40 to 60 rpm. Beyond that speed the watt governor will not work efficiently. Okay, so you can say that when the sleeve length is decreasing, when the sleeve is going upward, then the fuel supply must decrease. As omega is going to increase, then the fuel supply must decrease. So here why fuel supply is decreasing, but why the efficiency is not going to maintained. Okay, so it is that the solution is that generally when we look at this governor, the distance between the sleeve is very less, that is delta h is very less. That's why we cannot we cannot accurately we cannot say that this much amount of fuel must be controlled. Okay, so that is the thing. So now what the porter did, porter placed a mass m on the sleeve. Okay, porter placed a mass m on the sleeve. Now if you place that mass m, does the omega of the porter governor will increase greater than the guard governor? We shall see. Okay, generally when we look at the diagram, there are certain things which is done on the which is done in the diagram. So the arm E is placed at certain eccentricity. All right, so at that point we are considering the mass. Therefore mg plus f by 2, mg plus or minus f by 2 plus or minus I can say that this thing plus or minus will be seen in the sensitivity of the governor. Okay, so mg plus or minus f by 2. So f is the friction between the sleeve and the spindle. All right, so in the previous governor we didn't assume this mass of the sleeve, right? So therefore if we assume the mass of the sleeve, then there will be different things. Okay, so once we take the moment about eye center, we can form one equation. Okay, omega square equal to 2 mg plus or minus f plus 1 plus k. What is k, sir? K is tan beta by tan theta, tan beta by tan theta, that is k, right? So if k is now we have to now we have to compare the difference between the watt governor, speed of the watt governor and porter governor, right? So to compare the thing, if we consider the k as 1, then theta equal to beta. For theta will be equal to theta, there is one condition that the lengths must be same. The arm length must be same, and if there is an eccentricity, then the upside will must be an eccentricity. If this is directly connected to the axis, then it is must be upper link must be connected to the axis also. So that is the main thing. Okay, if you consider the friction between the sleeve and spindle is negligible, then we'll get one another relation. Okay, we'll get one relation like W of the Porter governor will be equal to M plus capital M by small m into W of the Watt governor. Okay, then the Porter by Watt will be equal to greater than 1. So Porter governor, of course, the speed of the Porter governor is greater than the Watt governor. So this is the analysis which is made by using this simple geometry. Okay, so generally now we are discussing about the governor terminologies. Okay, different terminologies which are used in the governor. First of terminology is that controlling force. Okay, controlling force. uh, when we are discussing these terminologies, we compare these terminologies with each other, and also we will discuss about the what is the effect of these terminologies and what is the reason for these terminologies and how these terminologies can be what is the meaning of these terminologies. Okay, so generally when we look at the controlling force is generally what is controlling force. That is the total resultant of the all the forces. That is a total resultant force. Suppose weight of the sleeve, if we consider the weight of the sleeve, if we consider the weight of the balls, if we consider the friction and centrifugal force and all, so the resultant of this all these forces is known as weight. No, not centrifugal force, but the resultant of all the forces which regulate the movement of the governor balls is known as the force of controlling force. Okay, so as we can see the controlling force, that what is the direction of the controlling force, that will be towards the axis of the rotation. What does this mean? It means that as we are going to increase the radius, then these controlling force, the resultant of the force, will try to pull that balls towards the center, right? This is the force. So as the radius is going on increasing, then the controlling force is going to increase. In the gravity control governors, these controlling force, the curve which is plotted from the force and the radius, it will be curved parabolic. Okay, if you want to draw the slope, tan theta will be equal to change in this fr controlling force divided by radius will use the slope of this curve. Okay, so in the spring controlled governor, it is a straight line, ar plus b. Okay, a b are constants, and these are found out from the from derivating the boundary conditions. Okay, so this is the thing about the controlling force. Now let's talk about the centrifugal force. What is centrifugal force? Centrifugal force is due to the rotation of the balls. Okay, when the balls is rotating with certain radius, the outward component of the force will try to pull these blocks. Okay, the tendency of the centrifugal force is to pull the block toward outwards the axis. Okay, so the direction, you know that it is away from the axis. Okay, it is opposite to the controlling force. Now if you compare these two forces, so look, first of all let's discuss deeply about the centrifugal force. As the omega is going to increase, then the radius is going to increase, the sleeve will move upwards, right? The centrifugal force is going to increase. So when we plot the graph, it will be straight line from starting from 0. It will not start from somewhere. Okay, starting from 0, it will, you know, there will be straight line. Okay, the slope is given by fc by fr, d by dfc by dfr. Okay, this is the slope. Now as we are going on increasing the omega, that theta is going to increase, right? Theta is going to increase. What is theta, sir? Theta is the slope is going to increase. This thing we need to know. Okay, so what is the difference between the centrifugal force and the fc and fr? So fr, it tries to pull the block towards the center, and centrifugal force tries to keep the blocks away from the center, right? So these two forces are opposite. Okay, at one point these two forces will be equal. At one radius these two forces will be equal. So how to find out the radius, sir? Generally, to find out the radius, you just draw the one point. When we draw the graph, there will be point of intersection of these two functions. Okay, at that point we can say that the force is equal, and also the radius will be equal. At one radius, at the forces will be equal. So when this fc will be equal to fr. So that is the thing. Now the according to the mathematics, there will not be any two functions. There will not be two outputs of any one input, right? According to mathematics. But when we see, if it is cutting at 2 points, it will not cut at 2 points, first of all. So it means that at two radius the forces are equal. So how the forces will be equal? Now let me tell you practically that suppose radius is r1, radius is equal to 1 centimeter, suppose say, okay, 1 centimeter or 5 centimeters say. So at 5 centimeters then the centrifugal force will be different and inward force will be different, sir. Okay, inward force will be less when compared to centrifugal force. Okay, as the radius is going to increase, then the this force, the fc is going to also going to increase, and that also going to decrease. Okay. mm. All right, so at one point the now there is a linear variation of centrifugal force, right? So when there is a linear variation of centrifugal force, like suppose if the radius is going on increasing, then centrifugal force goes on increase. But when we talk about the resultant force, that is controlling force, at one radius it is the force is going to increase gradually at one particular radius, right? So from this uh, we can say that as the radius is going to decrease, then that controlling force is decreased casually, but this centrifugal force will decrease linearly. So as we can say from here, we can say that at one point only, at one radius only, the centrifugal force must be equal to the that controlling force. It will not cut at more than 2 points, because it is violating the function, violating the law of mathematics, that is functions are derived from the sets and relations. Relation for a particular in the particular set, relation is satisfying only one thing. Okay, function for one input there can't be multiple outputs. That is the function tells. Okay, when you say f of x square uh, is a function or not, y equal to x square is a function or not, x equal to y square is a function or not, x equal to y square is not a function. Okay, y equal to x square is a function actually, because x equal to y square is not a function, because the graph is cutting, there are multiple outputs. For a function, there must be a single output. Okay, this is the thing. So now let's discuss about the types of equilibrium, to for the stability analysis of the governor. So generally, when we look at the types of equilibrium, first of all, there is a stable equilibrium. If the if the system returns to its initial equilibrium position, we can say that it is in stable equilibrium position. Okay, minimum work must be done on the system, to bring back the system to the stable. Okay, so unstable equilibrium, so within the disturbance of the, when we disturb the equilibrium, so when we disturb the system, so the system will not come back to its initial position itself. It is known as stable equilibrium, unstable equilibrium condition. To bring back the system to the equilibrium position, we must do a maximum amount of work must be done on the system. So third thing is that neutral equilibrium. So neutral equilibrium, the system will always in the equilibrium is known as neutral equilibrium. So now stability analysis of the governor. So what is stability of the governor? Stability of governor gives us an idea that governor is working or not, right? The governor is working or not. Suppose for example, there are in the governor terminologies there are two forces. One is controlling force, one is centrifugal force. Controlling force must be the slope of the controlling force must be greater than the slope of the centrifugal force. If the slope is greater, then we can say that governor is stable equilibrium condition. Once we look at the graph, sir, generally when we draw the graph, there will be one point where these two graphs will intersect. These two functions will intersect. That point is known as equilibrium point. That point tells us that forces are same, and also the radius of the radius will be same. At one particular radius, the forces of the forces, that is centrifugal force and also controlling force, are same. So when the slope of the Fr, controlling force, is greater than Ft, so when we take one force which is greater than the required radius, the radius which is greater than the required radius, then we can say that Fr is greater. Once the Fr is greater, then we took the radius greater than the radius which is in equilibrium, right? Which is optimum radius. We took the radius which is greater than the optimum radius, so it must come back to its optimum radius, right? So the radius must decrease. So actually the Fr is greater, it means that tendency to bring back the balls to its initial radius is greater, is going to increase. That's why the balls will try to come back to its optimum position, optimum radius. and and also when we are decreasing the radius, then the required optimum radius, it is greater, right? So radius must decrease. So when we see that centrifugal force is greater when we are decreasing, the centrifugal force tries to move the balls away, right? So it is going to increase the radius, that balls will tries to come back to its optimum radius. So this is the stable equilibrium condition. Now now when we talk about the unstable equilibrium condition, the unstable equilibrium condition, to force, the slope of the Fr is less than the slope of Fr is less than the slope of Fc. That is the centrifugal force. It means that when we are going to increase the radius, then the balls will try to go away, and when we decrease the radius, balls will try to come back, come to the axis of the rotation, come closer to the axis of the rotation. So this is an unstable condition. All right, so generally when we look at the omega, if the omega is going to increase, we have plotted the graphs, okay? If we are going on increasing the omega, so fc will not, fr will not increase or decrease. Fr is constant because fr depends upon the fc, and fr depends upon the mass and mass of the sleeve and uh, the mass of the balls, right? It does not depend upon the omega. So that's why, as we can see that slope, if we increase the omega, the slope of the centrifugal force is going to increase. So f required is going to increase, right? F required is going to increase. So it makes some sense, okay? For stable condition, we can say that the if omega is going to increase, then the slope of the centrifugal force is going to increase. Omega require R required is going to, R optimum is going to increase. So when we talk about the unstable condition, then the R required is going to decrease, okay? R optimum is going to decrease. All right, so this is the condition for unstable equilibrium. So generally when we talk about the spring control governors, there will be certain spring force, right? So that function is given as ar plus b. So b, there will be initial, there will be offset in the graph, okay? So as we can see that fr is less than the fc, the slope of fr is less than the fc. So therefore this is an unstable condition, okay? If we take the slope of the fr as theta r and slope of the fc as theta c, then your theta r will be less than the theta c. So this is the thing. So now what we are doing, we are providing offset below the line, okay? So b is actually, when we are doing in such a way that b is negative. If b is negative, it starts from the line. So fr, slope of fr will be greater than, so now it will become the stable equilibrium condition. Now another is isochronous governor. When the v is equal to 0, then this is condition for the isochronous governor, okay? In the isochronous governor, at any point, at any speed is constant. At any point, any speed, the balls will rotate with same speed, with the same radius. Balls will rotate with, at any radius, we can say that the forces are equal. At any speed, the forces are equal. All right, this is the thing. Radius are not same, but at any radius the speed is constant, right? This is the condition for the isochronous. The governors which are at neutral equilibrium, those are governors are known as stable isochronous governor. So generally from this we can say that stability of the governor is nothing but whether the governor is working or not. So for the governor to be working, then FR must be greater than 0. It is greater than FC, but FC will be somewhat it has one value, but FR must be greater than 0, okay? And also when we talk about the spring control governors, then we can say that A into R minimum minus B must be greater than 0. If it is greater than 0, R minimum will be is greater than B by A. This is the condition. So generally when we look at the when we revise the spring control governors, then we can say that A and B are the constant. These constants are determined from the boundary conditions, right? So if A is positive, B is positive, then this condition is for unstable condition. If A is positive, B is negative, then this is stable condition. And A is 0, B is B is 0, A is positive, then we can say that this is the condition for isochronism, okay? So this is the thing. So when we discuss about the stable and unstable isochronous governors, generally unstable governor, Hartnell governor, in case of Hartnell governor, we are decreasing the FR. If we decrease the FR, it from unstable condition to it becomes isochronous, from isochronous to stable. Sorry. So we are decreasing the FR. So FR depends upon the weight and mass of the balls, right? In case of the Porter governor, in case of the ward governor, what is going to happen? So there we are going to increase the FR or decrease the FR. There we are going to increase the FR. We take the ward governor, sir. Ward governor, so there MR omega square will be more. It means that FR is less, FC will be more. If FR is less, FC will be more, then we can say that it is unstable equilibrium condition, right? So therefore Porter introduced the weight. If he introduced the weight to increase the FR. If we increase the FR, then the slope of the FR is greater than the slope of the FC. Then it becomes a stable condition. Okay. So therefore the thing is, the idea is to increase the speed, increase the range of the speed. Okay. So that is the concept of the Porter. Okay. So now here we want to decrease the FR. So if you want to decrease the FR, then do the one thing, that decrease the weight in case of spring control governors. Okay. So this is all about the stability. Now we shall talk about the sensitiveness. Sensitiveness is nothing but ability to sense the change in input load and change the fuel supply accordingly. Okay. So this is the sensitiveness. So it is defined for the not connected to the prime mover and connected to governor. We are connecting the governor to. If we are not connecting the governor to a prime mover, then the sleeve displacement, whatever will the sleeve displacement must be more. Okay, the sleeve displacement, even for the less change in the speed, there will be largest displacement of the sleeve. Okay, so we are not concerned about that. So if the governor is said to be sensitive, when it is not connected to the prime mover, the sleeve displacement is more. Okay, it must sense the speed. We can say that it is sensitive. But in case of it is connected, if it is connected to the load, then the speed of the prime mover must be kept constant. So if the speed of the prime mover is kept constant, then it must be kept constant. So the sleeve displacement must be very less to avoid the fluctuations. So the better governor, the sensitive governor, is nothing but the governor which has less fluctuations. Less fluctuation in the sense the sleeve movement must be very less, as much as possible. Okay. In practical situation, when we see the load is going to increase, then speed, then the load is going to increase, then the omega will decrease. Once the omega will decrease, sleeve will come back to its come down. So the radius will decrease. Once the radius will decrease, then fluid supply is going to increase. So there will be fluctuations, right? The sleeve is going to increase or decrease. So the governor is said to be sensitive with the sleeve is very less. The sleeve distance must be as less as possible. I am not telling that in the governor's place sleeve displacement is very less, but we must to satisfy the condition of sensitivity, we must keep the governor in such a situation that the sleeve displacement must be very less to say that particular governor is sensitive. So I think we discussed up to the sleeve displacement, right? So sleeve displacement gives the sensitivity when the governor is we are talking about the governor is connected to the prime mover. Is governor is connected to prime mover load. So due to a variation in load, there will be variation in speed. Due to a variation in speed, there will be variation in sleeve displacement. Due to a variation in sleeve displacement, due to the mechanism, the fuel supply will change. Okay, and radius is changing. So when we put all these things into one picture, we can come to know that the radius is going to the change in the radius is very large. That is, the sleeve displacement is very large. If the sleeve displacement is very large, then we can say that governor is less sensitive. If the governor is less sensitive, then we can say that governor is more stable. So sensitivity is inversely proportional to the 1 by stability. Okay, stability is greater, its sensitivity is less. Sensitivity is less, stability is greater. Okay, these are the things. So generally, sensitiveness for the isochronous governor. When you talk about sensitiveness for the isochronous governor, omega is constant. Okay, at each and every point, the forces are same. So sensitivity, if it is no load condition, like we are not supplying to the connecting to a prime mover, then sensitivity will be infinity. If we are connecting to a load, sensitivity will be 0, but that is very less. If it is very less, then it is highly stable governor, we can say. So if the sensitivity is more, then it is less stable governor. So generally what happening, if we take the two governors, sir, that graph indicates the two governors. Okay, the F1 F2 curve which indicated by the black line indicates that FR, right? So when we look at the governor 1 and 2, I was discussing about this thing. So when you look at the governor 1 and 2, governor 1, let omega a be the speed of governor. Okay, if we increase the speed, then the range, the R optimum will increase, right? The range of the R optimum, it will be delta R optimum. Okay, delta R optimum for the first governor is more when compared to second governor. It means that generally if the R optimum is less, can we say that governor is less sensitive? So governor 1 is more sensitive than governor 2. Sorry, governor 1 is more sensitive than governor 2. Okay, within the if you increase the force, then the sleeve height is going to increase, right? The radius is going to increase. Radius is With the radius is increasing, then sleeve height is increasing. Okay, the sleeve height is also increasing. So that's why we can say that the governor 1 is more sensitive than governor 2. Between the two stable governors, the governor which having a larger controlling force at any radius will be more stable. Okay, so if you increase the controlling force, then the stability is going to increase. So from unstable to stable, if you want to convert from unstable to stable, then we are going to decrease the controlling force, right? So again, from stable to more stable, if you want to do, then we can increase the controlling force. So the last topic for today is hunting. Okay, so I think we discussed about sensitivity, right? All right. So generally when we discuss about the hunting, what is hunting, sir? Governor will oscillate violently to the extreme position, that is known as hunting. So generally there are two types of equilibriums, right? Two types of governors. We see stable governors and unstable governors. Generally when we look at the stable governors, when the load is increased, suppose for example, when we are going to increase the load, then uh, then what happens? The omega will decrease. Once the omega will decrease, the radius will decrease. Okay, it decreases from R optimum. Suppose the radius is at R optimum, right? So radius will decrease. Once the radius decreases, then the force which is mr omega square, that is fc try to, you know, try to bring back to its optimum position. Okay, due to the support of inertia, so it will go back from optimum conditions to again the radius increases. Now FR comes into picture and FR tries to take the balls towards the optimum position, R optimum. So again, due to the inertia, support of inertia, it goes from R optimum and also it reduces. So so how the it comes back to its R optimum. So when the friction is there, so friction is going to reduce the oscillations, right? So it will come back to its of V optimum. So generally when you look at the unstable conditions, sir, if we decrease the load, if we decrease the load, then R will increase, R omega will increase, omega will increase, then centrifugal force will increase. Once the centrifugal force will increase, then R radius will increase, and it goes back to its, the sleeve will rise and it moves towards the top dead center. And again from the top dead center, if you want to reduce the force, we will generally we are giving some disturbance, so we are decreasing the omega. When we decrease the omega will decrease to the zero. Okay, again radius is going to decrease, again the sleeve comes back to its BDC, again we are going to create disturbance. So this how it is going to oscillate from extreme positions violently. So these oscillations are known as hunting. When you talk about isochronous governor in these two governor, isochronous when it is connected to the prime mover, so prime mover sensitivity is zero. If the sensitivity is zero, sir, then generally can we say that the stability is more. So if the stability is more, there is no movement of the sleeves can be seen. The isochronous is connected to the without prime mover, then sensitivity is infinity, then stability will be very less. Alright. So this how we can say that isochronous governor is also hunting will takes place. So in the governor one, we have discussed up to the sensitiveness, right? So now we will discuss about the effect of friction. So generally when the governor sleeve is running at equilibrium position, there will be no sleeve displacement, right? Omega will be constant. So generally when we look at the friction, there will be three cases of friction. Once the friction is zero at equilibrium position, where the omega is rotating at omega optimum and r optimum, and actually when the sleeve is moving upwards, then there will be friction, right? Then mg minus f will be upwards, okay, mg plus f. If sleeve is moving upwards, then the friction will be downwards, then mg plus f. If sleeve is moving downwards, then friction will be upwards, mg minus f. Okay, this is the three cases. So generally what happens if we talk about the block on the vertical surface. So suppose the friction is 0.1 and the weight of the block is 10 newtons, then the frictional force developed mu square mu n will be equal to 5 newton. Okay, so when I apply 1 newton, the block will not move, what frictional force will be there. So limiting frictional force will be 4.99 newton. Okay, so when I apply the 5 newton, then the block will just will be in the impounding motion. Okay, when I apply 5.01, then the block will be sliding. So there are three cases of the block, right? See, one is body is at rest, body is at impounding motion, body is sliding. So now here itself there will be some friction, there will be some limiting friction. Now to overcome the limiting friction, some force must be applied in the opposite direction. To overcome the limiting friction, some force is applied in the direction. So that force is comes by increasing the omega. So let's suppose, for example, let 3 radians will be the change in the omega required to overcome the friction. 3 radians. Suppose my omega optimum is 330 radians per second. So when I increase to 33, the friction will overcome. Okay, so then the sleeve will move upwards till 31, 32, 33. Sleeve will not move. Similarly, if we talk about the minimum range, that is 28, 29, then sleeve will not move downwards. Then if it is 27, it will it is just to move downwards. Okay, so that is the thing. So this is the range. So depending upon this range, the sleeve will not move. Sleeve will not move means radius will not move. Radius will not move means the throttle valve will not supply the fuel. So if it is not supplying the fuel, then it is leads to the insensitiveness of the governor. Okay, that is due to friction. Generally this can be seen in the spring type governors. Okay, spring type governors, when there is a frictional force between the spring and the spindle. So that if that is considered, then there will be insensitiveness in the spring control governor. For that we have to release an initial compression of the spring. Okay, that is the thing. So if you see at the figure, there are three cases. So these three cases can be visualized. So change in speed to overcome the friction, omega can be given as omega a plus omega b by 2. And also coefficient of effectiveness, like sensitiveness, coefficient of sensitiveness, it is given by omega a minus omega b times 2 by omega a plus omega b. If it is isochronous governor, then 0 by something. 0 by something is 0. If it is 0, then stability will be maximum. Okay, that is the thing. Now effort of governor. Generally, to change the 1% of 1% of speed, whatever the force which is applied by the governor is known as effectiveness of the governor. It is given by 5 by 2, because it is taken as arithmetic mean, because the omega is very small. So when we talk about the power of governor, the energy which is required to which is when the work done by the effective is known as work done, power. Okay, so F times displacement, F by 2 times displacement gives the power. It will be in joules. So Hartnell governor, you can see the Hartnell governor. So there will be balls, there will be 2 arms. Okay, and with the help of the moment at O, moment about fulcrum, you can find out its magnitude, find out its forces. Okay, spring force. Spring force is again written as F equal to K times X. So this is about governors. There are some questions. Okay, these questions are discussed in the analysis when I am doing the analysis of volume 1 and volume 2. Okay, and that I will create an extra audio. So this completes my governor.